Hey everyone, welcome to The Explainer. I'm absolutely thrilled to be your guide today as we decode what is frankly one of the most critical documents in the electrical world. We're looking at the ultimate blueprint for building a fortress of electrical safety, and this is drawn directly from the AS/NZS 3000 2018 wiring rules, specifically Section 2, which covers general arrangement, control, and protection. Let's get right into it. Okay, let's dive into this. Have you ever just stared at a wall outlet and wondered, what actually stops your house from bursting into flames? It's a totally serious question. We pump massive amounts of raw, invisible energy right through the walls of our homes and workplaces every single day. Without the proper defenses, electricity would be more than happy to turn your cozy living room into an impromptu campfire. The stakes are incredibly high here. A poorly arranged electrical system basically invites disasters like thermal degradation, electromechanical stress, and, of course, severe shock. The rules we're exploring today, they are the exact mechanisms that stop all that from happening. So, to build this fortress of safety, we're going to break the installation down into 4 main parts. 1. Arranging the electrical installation. 2. Taking control and isolation. 3. Protection against invisible threats. And 4, the switchboard command center. All right, part 1, arranging the electrical installation. The standard explicitly states that an electrical installation has to be systematically divided into separate circuits. But why do we do that? Well, it's really all about containment and resilience. Think of it as the foundation of your fortress. First, we divide circuits to avoid danger during a fault. If one part of the system has a catastrophic failure, we want to contain that damage locally, right? Second, it minimizes inconvenience. We set things up logically so that if, say, your toaster shorts out in the kitchen, it only trips the power to the sockets. You aren't left standing completely in the dark because your lighting circuit is entirely separate. And finally, we absolutely must segregate safety services, like emergency lighting or fire pumps, from the general wiring. Because if the regular power goes down, that life-saving equipment still needs to run. Moving on to part 2, taking control and isolation. Think of these as the gates and drawbridges of our fortress. When we isolate an electrical circuit to work on it, we obviously want to sever the live power lines, the active conductors, so the person doing the maintenance doesn't suddenly start glowing in the dark, right? But here's the thing. The standard is incredibly strict about this. An isolation device must never, ever interrupt an earthing conductor. Why? Because that earth connection is your absolute vital lifeline. It gives fault currents a safe path to escape into the ground instead of traveling through a person. If you cut the earth, you are quite literally disabling your ultimate safety net. And this brilliantly illustrates the whole concept of the master kill switch. The standard states, the supply to every electrical installation shall be controlled on the main switchboard by a main switch or switches, because every fortress needs a way to pull up all the drawbridges at once. In an emergency, like a fire, emergency services personnel have to be able to walk up to the building, find that main switchboard, and cut all the power instantly. These switches have to be prominently marked and easily available. No confusion allowed when seconds count. Now, sometimes control needs to happen right at the machine itself, which brings us to emergency stopping. The rules lay out a very specific action sequence here. First, the device has to manually open the circuit. Second, and this is absolutely vital, it must literally latch or be physically restrained in the stop position. It locks into place. And third, it demands a manual reset before anything can be restarted. This way, if you slam the emergency stop on, say a massive industrial saw, the thing doesn't just unexpectedly jump back to life the second you let go of the button. You have to consciously, manually reset the system once the danger is actually gone. Which brings us to part 3, protection against invisible threats. In this section, we deploy the guards, and the primary invisible threat these fortress guards are constantly scanning for is called overcurrent. This happens when the current exceeds the safe limits of the live conductors, which causes excessive temperatures or electromechanical stresses. To put it simply, it's the threat of melting wires and starting fires. Protective devices have to automatically sever the supply before this overcurrent can reach a dangerous magnitude. Now, what's really interesting about this slide is how the standard breaks overcurrent down into 2 very distinct enemies. On the left, we've got the overload current. This is your slow burn. It happens when you run too many perfectly healthy appliances on a single circuit at the same time. Plugging in a space heater, a microwave, and a hairdryer all at once. The wire just slowly, gradually heats up. But on the right, we have the short circuit current. This is a sudden, explosive, violent fault happening directly between conductors. It's over in milliseconds. Our electrical guards, the circuit breakers and fuses, have to be perfectly coordinated to detect and defeat both the slow burn and the violent explosion. But here's the catch. Circuit breakers aren't actually enough to protect humans from a shock.
That is why the rules heavily mandate the RCD, or residual current device. Let's cut through the jargon for a second. An RCD is essentially the ultimate reflex system of your fortress. It constantly monitors the current going out on the active wire and coming back on the neutral wire. If it senses that power is leaking out of the system, meaning less is coming back than what went out, it assumes that current might be leaking through a person into the earth.
And here is exactly how that disaster gets averted in real time. Step 1. A fault occurs. Imagine a wire inside your washing machine jiggles loose and touches the exposed metal frame. Step 2. The RCD detects this leakage. In a residential setup, if it hits just 30 milliamps, which is a tiny, tiny fraction of an amp, it triggers. Step 3. The RCD instantly severs the power. It achieves automatic disconnection of supply in mere milliseconds, literally saving a life before a shock even has the chance to become lethal. But there is a catch to how we deploy these life-saving RCDs, and it's beautifully represented by the number 3. Under the NZS 3000 residential rules, 3 is the maximum number of final subcircuits that can be protected by any single RCD. Why 3? Well, we go right back to minimizing inconvenience. If a faulty toaster trips an RCD, and that one RCD was guarding your whole house, you'd plunge the entire place into darkness. By limiting it to a max of 3 circuits per RCD and requiring at least 2 RCDs per house, a single fault stays totally contained while the rest of your fortress stays illuminated. Finally, part 4, the switchboard command center. Because this is the command center, there can be absolutely zero ambiguity about what it is. The rules are crystal clear. It shall be legibly and permanently marked main switchboard. If smoke is pouring into a building or a technician needs to kill the power right this second, there's just no time for guessing. The command center has to be immediately identifiable to anyone, especially emergency responders. So the crucial point is that a command center is really only as good as its location. The standard gives us a strict list of forbidden zones. You can't put a switchboard near baths or showers, what we call zones 1 and 2, because high humidity and moisture are the mortal enemies of electrical safety. You can't put them inside fire-isolated stairways either, because if a fault in the board creates smoke, it fills the exact path people are trying to use to escape. And you definitely can't just shove them into the back of a cluttered cupboard. If they're in a cupboard, they need dedicated, front-facing space. Clutter is a massive hazard here. Building on that, the accessibility rules are totally non-negotiable. The switchboard has to be entirely unobstructed by the building structure or any fixtures. You need adequate space on all sides so a technician can stand safely, operate the switches, and actually do their maintenance. And crucially, there must be clear emergency exit facilities. A command center is completely useless and honestly a bit of a trap if you can't reach it safely to cut the power, or if you can't escape from it quickly when the equipment itself starts smoking. And that brings us to the end of our decoding of Section 2 of the AS/NZS 3000 wiring rules. We've seen how arranging circuits builds a solid foundation, how proper isolation acts as our drawbridges, how RCDs and overcurrent devices stand guard against those invisible threats, and why the switchboard has to be treated as a pristine command center. So I'm going to leave you with this final, provocative thought. When was the last time you checked your own home's command center? Is it easily accessible, clearly marked, and equipped with the right guards? Thanks for joining me on this explainer, and keep your fortress safe.